Okay, welcome everybody. I hope you all had fun. Oh, hi Pete. Hope you had fun last night. Welcome back. We've got a full day ahead. Before I start my session, I've just got a couple of things to say. First of all, we want to get a group photo. So at break, before you grab pastries and coffee, if you can make your way outside, and we're going to do a nice photo on the steps. Apparently, there's going to be sunshine this morning, so we want to grab hold of that. The second thing is we are going to do posters at lunch. So, and there's going to be poster presentations, and they're going to be at 1:30. So when you go out for lunch, you can grab some food, but then please do go along and have a look at some of the posters and hear some of the short presentations. And I think that's all the announcements. So yeah, session 3. So yes, yesterday we were looking back, the 25 years of the Centre for Water Systems and some amazing things that have happened. And today we're going to be looking forward and thinking about research for the next 25 years. So we've got talks and we've also got workshops. And I said we've got the posters. But let's get the first speaker up on stage. Can I please welcome Raziyeh Farmani?
Good morning. I've decided to talk about self-healing and what does it mean in water sector. Last year we attended a workshop and we were asked to say how self-healing water pipes will look like and are we doing right things to get there. So my talk is kind of introduction to a workshop that we have organized and it will take place after the coffee break. So self-healing, the concept comes from the biological systems. So when we have got a cut, blood comes and clots and blocks that, so it doesn't allow it to deteriorate further. It is taking a lot of other sectors are taking advantage of this concept and building very advanced methodologies. For example, computer science is doing a lot. So if we have got a system that has got some failure or intentional or malicious attacks, it's got measures in place that recovers and gains some normality. Now, with advances in material sector, there will be some opportunities for water sector to take advantage of these computer science knowledge as well as material. Why is it important? Time and time again, we hear how aging assets are failing and causing a lot of disruption. In addition, we have got climate change that is impacting our buried assets and causing a lot of other issues. So, for example, currently we are in a situation 20% of the water is leaking in UK because our assets are not in a good condition and we are losing valuable water that's got a lot of embedded energy in it as well through leaks. In addition, population is growing, demand is increasing, so it's very important that we have got supply-demand balance, balance it through other ways rather than relying on exploiting additional natural resources. So what are self-healing systems? So if we have got a system under normal state, it's functioning very well. And if we do some kind of maintenance, it will stay in that state for some time. However, if we don't look after our assets, eventually they are going to deteriorate and move to the degraded state. We may have some capability to detect deterioration in our assets and do some predictive maintenance, not to allow them to further deteriorate. And also, we may have some capability in our systems that self-protects itself and recovers from degraded state, more like operational self-organizing, and goes back to their normal state. However, if we don't maintain our systems, these degraded systems eventually are going to fail. And if we have got access to advanced computer science or materials, we may have systems that can detect that system is starting to fail and somehow self-heal and go back to some normality. Looking at other sectors, for example, oil and gas, they are looking at different pipes with different coatings. So, for example, they have got some pipes that have got layers of these liquids that have got self-healing agents, and they are activated. If there is some damage in the pipe, it starts triggers the activation of these self-healing agents, and they start healing the parts of the pipe that are damaged. In some cases, it does without any assistance. In some other cases, they have to do some support in the form of warming it or some other human input to be able to activate that self-healing process. So in water sector, there are, in last couple of years, more studies. For example, currently there is a study in Australia. They are looking at self-healing wastewater concrete pipes. And the concept behind that is to use sludge to basically, as well as contributing to the circular economy, not sending it to the waste, using those as self-healing agents in the concrete pipes. Another trial was carried out at Northumbrian Water in UK last year, and the idea behind this one is identifying that there is some damage in the pipe. For example, pipe has got a leak, etc., and injecting some kind of water gel minerals at the upstream of that pipe, and eventually this will go and fill those gaps and protect the pipe. To some degree, these kind of concepts, because they have, especially the one that's been trialed in Northumbrian Water, it's assisted self-healing. And we have seen some of this in the past. For example, around 15, 20 years ago, it was very common in UK. Water companies, asset management was cleaning the pipes and relining the pipes. So no dig, like the figure at the left, right-hand side. They were opening the chamber and passing the lining through the pipes. And when water was pressurized, this was creating a layer of protection for the pipe and blocking some of the leaks and improving the water quality. However, it seems that in the water sector, based on existing assets, because we are not going to be able to replace all the existing assets with, even if technology gets to the position that we have got self-healing pipes, we won't be able to replace all the existing pipes. So what does self-healing means for the existing pipes, which, for example, this pipe we are looking here is around 80 years old. How do we make sure these pipes are going to self-protect and be resistant against different changes that are happening to them? And from a water point of view for existing systems, I think self-awareness is the critical one. What does that mean? We are seeing more and more sensors coming to market. For example, currently there are a couple of pilots in UK looking at fiber optics in water distribution pipes. One of them was initiated by DEFRA in UK, and the idea behind this is that rural areas which don't have access to internet we can use existing infrastructure in water distribution networks, pass the fiber optic pipes, to, sensors through them to increase the internet accessibility for rural areas as well. In addition, it can collect information about the system, so leakage, quality, etc. Or also, there is currently a major research project in UK. They are looking at floating robots in distribution networks. And the idea behind this is these are going to be very small sensors, and they are going to float through the outer distribution networks, and they are going to provide data about the condition of our assets. And obviously, we've got traditional sensors, flow meters, pressure loggers, acoustic loggers. They can provide information. So the key thing is increasing the self-awareness in the system, identifying where things are going wrong, and then having some recovery measures in place. Some can be operational interventions, and some can be with some human interventions. So we have organized a workshop called Digital Solutions for Water Distribution Systems. The idea behind this is that to look at what we are currently doing. Are we ready when technology is available, very self-healing material is available, or computer science and extracting the best knowledge from these sensors? Are we in a position to be able to use and benefits of those for water sector? So the workshop that we have organized is going to take place in seminar room 4. And this is the format for this workshop. We will have 5 researchers from center. They are going to talk about their research that is contributing to digital solutions for water sector. We have got 5 panelists. They have kindly agreed to provide feedback, and also we are going to hear their views about how the asset management is going to take place in future, in next 5 years, in next 25 years. So panelists are Professors Kaplan, Kidwell, Liu, Savage, and Wanzil. So if you are interested, please join us in this session. And just before I finish, in the Center for Water System, we also look at intermittent water supply systems. Our current focus is more on transition from intermittent to continuous supply systems. But with global changes, population growth, demand increase, there is a good there is a danger that in future not only we may not be able to solve the solution, we may have more regions going under intermittent water supply system. So our focus on intermittent water supply system research is how to translate some of this knowledge to that sector, to see if it's possible to take advantage of lessons learned from continuous systems to leapfrog in the kind of intermittent water supply system to make sure we deliver good quality water for everyone. Thank you very much.
Yeah, so let me just see. So we've got time for a question, if we've got a question, otherwise we can keep going. Okay, I mean, there'll be lots of time for questions during the workshop, as there's a session that's dedicated to that. Brilliant. So our next speaker is Professor Guangtao Fu.
Good morning, everyone. I'm going to talk about how AI could help us build sustainable and resilient urban wastewater systems. AI means different things to different people. Andrew Ng, professor of Stanford University and co-founder of Google Brain and several AI companies, believe AI is the new electricity. So it will transform our society like electricity did 200 years ago. Sundar Pichai believe AI is bigger than fire and electricity. Do you agree with him? obviously someone doesn't. So the ex-car engineer, the co-founder of the Google self-driving car unit, believes AI is God. So he founded an organization to create AI-based God for people to worship. I'm not here to talk about how AI will help us, will rule, AI will rule the world, or how AI will help us, to achieve universal basic income, create a volley world. So I'm talking about how AI will improve the performance of urban wastewater systems. We heard Safe and Sure project several times, many times yesterday. So basically, the David Fellowship finished about 5 years ago. So one of the key outcomes from this project is the new paradigm for water management, building on the relationship between resilience, reliability, resilience, and sustainability, which are different aspects of system performance. Right? There are 4 types of data analytics: descriptive, diagnostic, and predictive. They help us to understand the system processes and identify, the failure patterns and predict the future states. Right? Together, they provide new information, knowledge, and insight about our water systems. On the other hand, we have a prescriptive analytics provide effective solutions to improve system performance. Before I talk about how it improves, the resilience and sustainabilities, so I wonder, what does the future, the sustainable, resilient water system look like? So do you have a picture in your mind? I don't know the answer, so ask the AI. So it projected this kind of, the pictures for me. How do you think of this? So there are many features we can see, connected, circular, blue, green, energy efficient. So it might be very difficult to predict what the future, wastewater system look like, but it has become very apparent, based on historical development. There are 5 pathways. Right? I'm going to talk about each of these 5 pathways very briefly, using one example from my previous work. Okay, the first one, greening. Green infrastructure, has been gradually, built into existing green systems. Provides multiple benefits, right? The flooding, the air quality, water quality, amenity, many other better. If you look at the flood damage curve, green infrastructure can help us manage more extreme, the flood event, like, this case up 100 years flood event. Right? But in order to build resilient, flood resilient cities, we need, to tackle a lot of challenges using AI, to integrate the green systems and to integrate, excuse me, to integrate the physical and the social systems, including, the community, the measures, resilient measures, social system. And we also need AI to help us monitor green infrastructure and look at long-term resilience and real-time control. I will use one example to show, the spatial impact analysis we did. So this, we conducted exploratory spatial data analysis to understand the spatial impact of green infrastructure on resilience improvement in the Topsham area. So we look at permeable pavement and bio-retention cells and the green roof. Also look at their combined impact. So you can see the red cells, basically they show they are very sensitive to green measures. So in terms of the resilience improvement measured based on, the CSO magnitude and CSO durations. The result shows if you look at the permeable pavement and the green roof have a high impact on resilience in terms of CSO durations, as you can see the figure here. And bio-retention tank, on the other hand, very effective for CSO magnitude. The second pathway, decentralization. Obviously, there are many, the on-site wastewater treatment technologies and commercial units available. So AI technology has been used, to support planning, operation, this kind of decentralized system. But here, talking about decentralized green infrastructure. So I have an example. He's from Dalian, a coastal city in China. So we have, we did a simulation with 31 sub-catchment with 5 meter resolutions. You can see there are some, low resilience sub-catchment in downstream here. So it shows by the colors. This curve shows the number of flooded cells changing during the flood event. Right. So we converted this curve into the bottom here, into the performance curve to calculate the resilience. Okay, so we look at different decentralization scenarios in order to improve flood resilience. We look at the 2 areas in particular. Area 1, each area has 2 catchments. Area 1, area 2. We look at the upstream to implement green measures in the upstream only, in the downstream only, and in the both catchment. So the result shows the upstream measures are very effective in area 1, but the downstream measures are very effective in area 2. However, if we look at the fully decentralized interventions are most effective for both catchment. The third pathway, decarbonization. So we all know the UK industry aims to achieve net zero by 2030. So, but there are many challenges. So the first one, so the greenhouse gas emission accounting. So we know the emissions from fuels can potentially contribute up to 20-30% of the total greenhouse gas emissions from the wastewater system, but currently they are not counted. So the on-site monitoring, we need new sensors and new data analytics. We have little knowledge about the greenhouse gas emission production process in the sewers and also in the wastewater treatment plant. So here I will use one example to show the potential of optimal control on carbon reduction. This work was done by Chris Apples, with Apples. So we look at a benchmark wastewater treatment plant. We applied multiple objective optimizations, considering the costs, greenhouse gas emissions, and water quality requirements. So you can see from here. So there are clear trade-off between cost and greenhouse gas emissions. Right? But there are some solutions at the bottom here, so they can achieve about they can reduce greenhouse gas emissions about 20% with a slightly increased the cost. So these solutions all meet the water effluent quality requirement. Right? So this shows the important optimal control. So the fourth pathway, the circular economy, we proposed a dual loop framework to improve resource efficiency and sustainability. So the outer infrastructure loop, we think it's important. We need to use the system approach, right, to understand the interaction between different systems, to integrate various urban water systems. The inner resource loop requires a deep understanding about the nexus between the 3 materials, the water, energy, materials. But the key challenge is to understand the interactions between the 2 loops, right, and the changing environment. So here's one example on energy recovery from wastewater treatment plant. We assessed over 300 control options to investigate the potential of energy recovery and its impact on sustainability. We used 6 indicators to measure sustainability from B, C, D, E, F, G. So A is the net energy use. So we wanted to minimize all these objectives to move the curve basically towards the center of the graph, right? So as a result, so if you look at this one, so it's possible to achieve energy neutrality through energy recovery, right? So but it have a negative impact on the sustainability. We have two indicators get worse, right, than the base case. The final pathway, the automation. So this is the key area we have focused on in the past with several, the PhD students working on this topic. You heard from Mariam yesterday, and Farmani here mentioned Chris with iPod already. So basically, what we did, we developed a number of the global control and integrated control strategies to investigate various problems like system resilience and consenting, and look at climate change impact, look at adaptation pathways. Right. So currently we have another PhD student, Chen Pei. He's working on the deep reinforcement learning, which are the emerging new technologies. So which have a very simple. So it trains an agent through the interaction with the environment, with the aim to maximizing the return, the expected return in the long term. Right. So feel free to talk to him. He has a poster outside. Right. So I just skip this one. So we need to bring all the 5 pathways together. So it is important to emphasize the key challenge. It's important to emphasize these pathways are not mutually exclusive. They are closely linked. Sometimes, like the greening, decentralization, decarbonization. So they are closely linked. So one intervention options could potentially provide multiple benefits and different pathways. So it's important to understand the synergies between different pathways and also to maximize the benefit using AI analytics. Obviously, AI technology has many, the features, as you can see here. So it's important to build tailor-made AI systems for specific water problems. Okay. So here is the overview of some water management problems which can be solved using deep learning technology. You can see I mentioned a deep reinforcement learning here, so can help us in many different the aspects. We have a paper if you are interested to read these papers. Obviously, there are many research challenges and practical barriers. We grouped this into 4 classes. Look at the 4 dimensions, cyber physical systems, institutional governance in the water sector, and look at the social, economic, technological development in the wider society. I don't have time to go through all of this, but I guess these are more than enough for all of us to work in the next 25 years, right? If you are interested. So, what should we be focusing at Exeter? So, my personal view is that we should, make best of our strengths, to accelerate the integration of water research with AI to tackle the environmental and societal challenges. We need to play a leading role in building disciplinary research communities across water, environmental, computer science, social science, and many other subjects. Right. So, just before I finish, I wanted to share one thought from Gary Kasparov. So, the world chess champion who played the famous game against the supercomputer, the Deep Blue. So back in 1997, you can see here is a weak human plus machine plus better process is much powerful than strong human machine plus inferior process. So do you agree with him? Or do you agree with me or not? I think in the future, we might need to treat AI as a team member rather than as a tools or algorithm. So a key challenge, to tackle the complex water systems, I think we need to develop leadership skills, to build a team where AI and human can work together, can complement each other through effective interactions. Finally, I want to thank all of my collaborators and colleagues in the past, in particular in the past 18 years at Exeter. Thank you.
That was brilliant. Thanks so much, Guangtao. I'm afraid we've got quite a shot to keep time. We haven't got time for questions, but we have got the break and lunch. So if that kind of sparked any questions, or you want to have a chat with Guangtao, then he'll be around for the rest of the day. So we're going to move swiftly on from AI to the water, energy, food nexus, natural next step. And yeah, please come along, Fayyaz.
Can you hear me okay? I have got this separate one here. The reason being, if I being here, then I will be losing myself because the background is too bright. So I thought to be in the limelight as well, a little bit on the side. Good morning. I am Fayyaz Memon, and my talk has got three distinct sections. Of course, they are interlinked. Very briefly, I would like you to be on the journey, the personal journey, very briefly. Then what I do in addition to water, energy, and food nexus, this is one of the things I do. And I'll be talking about both micro and macro scale, both in terms of spatial and temporal scales as well. And then the final part of my talk would be essentially one slide, giving us some reflection on what should be doing, what we could do, or what we should be doing with respect to Nexus approach. So going back, normally, sometimes I get some requests. I like everybody else to examine some PhDs here and there. Recently, I had one from Australia. And then the good thing about that PhD was each chapter was starting with a quote. So I picked two. The PhD was more on the water and energy multi-utility provision at a neighborhood scale, And then these quotes seem unrelated, but they are quite related here as well. Like connecting, everything is connected with everything else, which is particularly true with water and food and energy nexus as well. And Guangtao said about the processes, it's more about the journey, about the processes rather than the numbers, and sometimes you get the joy, and sometimes you are in a different mood. So it's more about the journey, I would say. So the personal journey, I was adopted, not only me, but my family as well, as part of the CWS back in 2006, which you can see on the left. Things have changed, and they have changed very visibly in all different directions. And here we've got 2023, we've got food, we've got water, and then I had some energy, but that energy was fizzled when I saw the bill. It was a family kind of a menu testing session, an Italian cook cooking for one of the events, which is coming as a family event, but then I have to pick the bill, and the cook is, Spanish cook, he is trying to cook some Indian stuff. So quite interesting stuff. So now there has been lots of change, but something has not changed a lot. I think the best person here to guess that would be perhaps David. David, can you see what has not changed? I can bring some laughter here. It's my accent, how I speak. So that brings a little bit of laughter, which you saw, and a little bit of misery to my wider family. These are some of my PhD students, and then they know how difficult it could be sometimes to deal with the pain and with misery while understanding me, where I'm trying to navigate to them. These are some of the postdocs. Obviously, it's not a CV show here. Now, what I do, essentially, I look into these different domains, urban water flows. Obviously, there is nothing, this is the urban water system. So my niche is more or less looking into the climate change adaptation. How? By integrating these individual flows, i.e. the infrastructure, not literally the flows, but the infrastructure, and making the most of the benefits that integration can bring by means of developing some technologies and then looking into the impacts they have or how they interact with the wider environment. And more recently, I am venturing into the analysis of the system of systems. That is, treating water as just one system and then venturing out to other systems. Like we have got, we need energy to produce water, and we need water to produce energy. We need both to produce food, and now the land nexus is adding a bit more complexity. There is a competing demand on land for biofuels versus producing foods and so on and so forth. Okay, so what we are going to talk about, essentially, just giving you a flavor of the processes. I've got 4 projects. Some of them have finished, some of them are running in different continents, in different countries, and then we pick up something on the scale issue. This is the very first one, which we did for Iraq, funded by the Iraqi government. What we looked at the micro scale, at a domestic scale, you've got different end uses of water, you've got different end uses of energy, and we eat lots of different types of foods, and then there are processes, hence there are energy implications. So we looked at the behaviors at a domestic scale, say from around 350 households in Iraq in different settings, looking into their demographics, socioeconomic conditions, and so on and so forth, looking into consumption behaviors, and then we came up with some interactions. Then we repeated the similar exercise on slightly larger scale, which was non-domestic scale, i.e. commercial sector, and then we moved on towards the supply side of these resources provision at a city scale at a different level. It's not about the numbers, it's more about the processes here, I would say. The next project is funded by the Indonesian government, and here our PhD student has been calling us. What we were aiming at, how water, energy, and food nexus is influencing the Human Development Index. Human Development Index is normally calculated or conceptualized on the basis of level of income, health, and education, how these things are influenced by the availability or lack of availability of these key resources. We developed a tool in MATLAB that is again a data-driven tool supported by MATLAB, which picks both negatives and positives, which the the water, energy, food nexus can have. And then not only that, after the fine-tuning the process, we went for some validation exercise as well. So some results are shown here. That's not the time to go into that. The third one, which I have, was kind of an undergraduate project, not even a PhD project, which is a different scale here, but quite impressive. He was my project student, and then he moved to the MSc level as well. Here, what we looked at, Spain is very famous for their agricultural produce throughout the world. So the focus has been, this is just the front end. There are lots of sub-models and interactions sitting at the back. This is just the front end, both focusing on the demand and supply side of these 3 resources and so on and so forth. And this time, what we did, we deliberately focus on food, looking into the diet kind of preferences, how land is going to be integrated into the whole assessment, and on top of that, how the technology penetration is going to influence one resource, i.e. food or energy or water to some extent. And then what we did, we applied that kind of a bigger tool using the Spanish version of climate change scenarios for carbon emissions and so on and so forth. And then we measured the performance or indicated the performance of the Nexus for policy derivation using a number of indicators. Again, the focus has been here on the performance. The quality of the output is very much dependent on the data. The fourth one and the last one, then I will be leaving you with a slide on what to do next or what we could do next and so on and so forth. The fourth one is an ongoing PhD, and I admire this lady, my PhD student. Just before going for her wedding ceremony 3 days ago, she managed to email me some slides just to save my soul. Okay, so what we did, so best of luck and best of wishes to her, which I'll communicate from you guys as well. What we did there, the bigger scale, when you look at the bigger side, bigger scale, then you mask the uncertainties, you mask the deficiencies. We have captured these things there. So what we did, we were very much privileged to have lots of Chinese data on different indicators, which we used to develop using those interactive data-driven models. And then we validated by means of backcasting. The validation was done for the kind of things like availability of water resource was called as the first validity. So what we had the climate change parameters. We use in a simulation tool called Joules, which takes climate influencing parameters into account and gives you some lots of hydraulic analysis. One of them is the surface runoff and so on and so forth. Using that one, we did some backcasting on how much water is used for crops, for energy, rural and domestic water supply, demand balance, and so on and so forth. And then we came up with yearly water scarcity or water security index for different provinces of China. Now here you can see there is lots of water availability on the graph on the right side. You can see that there is lots of water availability, but there are provinces where you can see a clear deficiency in water and so on and so forth. Using that tool, we applied this for a number of conventional climate change scenarios, not only those, but on top of that, we use the socioeconomic scenarios and combination of those. Again, the focus has been the process is going to be ongoing work. Let's see what comes out as a result of these scenarios on a longer scale, say 50 and 100 years forecast, and so on and so forth. Moving on, the last slide which I have here, where shall we be going? I give myself a pause a little bit here for you to digest, and then we may be able to discuss a little bit. So obviously, we are these days, we have the cost of living crisis. Obviously, it is going to influence human behaviors and so on and so forth. How it is going to permanently or temporarily influence the water and energy and food nexus, this is something can be looked into. Or as Guangtao was mentioning, circular economy, how an evidence base from water, energy, and food nexus can inform better planning for circular economy and so on and so forth, or how to look into the competing demands, as I said before, for energy provision via biofuels and limited land utilization for feeding more bellies. Okay, the multi-utility provision, again, how it is going to influence the whole nexus kind of thinking. More importantly, I think it is important that we have an appreciation, and I think we have the geopolitical realities which are emerging these days, like Ukraine war or Brexit. Some of our vulnerabilities have been exposed. How we are going to deal with those, perhaps the Nexus analysis can help us in that direction as well. The emphasis, the influence of new policies. The other day, at a local level for London, we got this ULIS ultra low emissions zone. How this is going to affect the whole thing, that could be looked into. Or even maybe a week ago, there was a news on BBC that there have been changes, amendments, or retracting the pollution control laws for new bids. So there are some resource implications that needs to be looked into, and so on and so forth. And more importantly, I would say the last one is the data collection frameworks. Otherwise, we have got the processes which are fine-tuned. Some of them are data-driven. Some of them are the real interaction that we have seen. Now, what is happening? If we have a consistent data collection taking place at intranational, among ourselves, or at international level on certain parameters in a consistent way, then the whole nexus kind of pie in the sky can be more evidence-based and more authentic. This is how I would think. Finally, I would like to thank you all, and especially my colleagues here, and CWS colleagues and everybody else for their contributions and making me feel part of the team, which is very much appreciated. I think one thing which is not highlighted either yesterday or today, our research effort and the critical mass on developing countries. Things are here and there, and a quite considerable amount of work. So Center for Water System has been contributing on developing countries. For example, I have got a number of projects in different countries in Africa. So is with Albert. So has been with David and other people. We have got intermittent water supplies. So there is a critical mass and good work, which is very much presentable and making impact, which is reflected in our rankings as well. The developing countries angle, we have been mindful of it, and it has to be in knowledge of the distinguished audience here as well. Thank you.
Right, we've got time for one question. If I'm going to put up the future directions, because I thought it was a nice slide. Oh, perfect. Let me pass you. Well, it's better if we use these, if that's right. Do you mind if we use like, yeah.
Thank you, Fayyaz. That was very interesting, and I liked your application of systems dynamic to the Nexus. And I wondered whether you've discovered any potential tipping points, either in a positive direction or a negative direction within those models.
I think the tipping point is very much linked with the consumption behaviors. And now we are seeing an additional tipping point with respect to cost of living crisis or something that is going to influence consumption behaviors. I think that would be a kind of a crisp answer, but we can talk about a bit more if you wish. And then the tipping point, having this nexus thinking coming into policy formation, would be tipping point would be the facilitation and ease of access to the data availability, which informs these complex models. That will be a tipping point. That will be a robust evidence base then. Yeah.
Brilliant. Thank you. Okay, wonderful. Okay, great. So our next speaker is going to be talking about heat energy from wastewater. So yeah, welcome to the stage, Mohamad.
Thank you. Thank you. Hi everyone. Today I'll be talking about heat recovery from wastewater. We'll start with some basics. If you're not familiar with the topic, you can understand the basics. And then we'll talk about existing work so far, what the challenges are, and then what we need to do in the next 10 plus years. So the concept is simple. You have a heat exchanger in the sewer pipe. You extract the heat, and this heat goes into a heat pump, and that will amplify the heat and can be used for heating water or space heating. Now, my area of research would be in this part here. So, where to locate the heat exchanger? Because when you extract the heat, obviously you cause a reduction of temperature in the wastewater. And this reduction can cause problems at the treatment plant, particularly with nitrification. Nitrification has to be done at certain temperatures. Ideally, you want the temperature at the influent to be 8 degrees Celsius or above. Below that, then you might need to, and it will affect your nitrification. So, early models have shown that when you recover heat, so the solid black line, that is business as usual with no heat recovery. If you recover, let's say 20 kilowatt, then the difference is insignificant. But if you recover 50 kilowatt, or 500 kilowatt, sorry, then there will be a large drop at the beginning, and then the temperature will increase because the heat is reclaimed from the surrounding air and soil, and you reach the business as usual case after maybe 1 kilometer of length. Why is heat recovery important? It's because the majority on a large portion of the carbon emission comes from heating, and the coefficient of performance, that is the ratio of output to input, because you are using electricity for heat pump. So the output heat over the input electricity, that is the COP of a heat pump. Currently, the government is promoting air source heat pump, but that has relatively low COP, around 2 or 3 value of COP. But in wastewater heat pump, you have 4 or even more than that. Sewers everywhere, and it's close to the heat demand location, and we have a large potential of heat from the sewer that is close to the consumer. Also, the heat recovery from wastewater can benefit in other processes. For example, the reduction in wastewater temperature may reduce the formation of hydrosulfide. So currently, this is the computational model. You have heat transfer between water and soil, and water and air. And the idea here is to simulate the temperature variation of the wastewater along the pipe profile, and therefore know the impact of heat recovery. So that's a single pipe model, and that is then applied on a network, a large 3,000 pipe network, network. The heat transfer between wastewater and in-sewer air, that is complex. And we have addressed this and managed to estimate it accurately. However, we apply this into a large sewer network of 3,000 pipes. What you see here in the horizontal axis, that is how much heat you can recover. And then in the two vertical axes, this is the temperature of the wastewater in the sewer pipe on the right, and at the influent on the left. So we have a threshold of 9 at the treatment and 5 degrees Celsius as the network, because you don't want to freeze the wastewater in the pipe. And anything, so any of the points above the dashed lines, that is a viable option for heat recovery. You can imagine the more heat you can you recover, the larger reduction in temperature. So that is a network model. However, what we have found is the modeling accuracy can sometimes be high. So this is a Taylor diagram. You don't need to be familiar with Taylor diagram. All you need to know here is that an accurate model will show a modeling error closer to 1, no more or less than a deviation of 1. So the closest to this point, the more accurate you model it. And you can see the model has performed well in the majority of cases. This is different models, actually, my model and other authors as well, at different months. We noticed that April and June has shown particularly higher modeling error for my model and also for the other models. 1 and 2 is just type 1 and type 2. So that is that suggests that there must be some missing process that we haven't accounted for, and the exact reason is not clear yet. So this inconsistency in modeling error needs to be investigated. We found also that the peak of heat recovery is lagged is lagged by around a couple of hours in comparison to heat demand. So if we can manage to store the heat recovery, that would enable us to optimize the heat recovery process and meet or attempt to meet the heat demand. What else? We don't know the financial return, and it hasn't been an applied published literature in terms of heat recovery from sewer network and how that can benefit stakeholders. So the future goal would be to advance the heat transfer process and investigate these uncertainties in modeling errors. We'll talk about each goal in more detail, and also optimize the heat recovery in spatial and temporal terms, and develop sort of the business model to estimate the financial returns and identify stakeholders. And then once that's all done, then we can apply it in a field study, because this is one of the main barriers towards the company, that they don't know how this is going to benefit them financially. So we need to improve the understanding of heat transfer processes and also adapt the model to be transient model, because when we consider heat storage and optimization, then the model needs to be transient. And we need also to develop a smart storage technique. And to do all of this, we need to apply the heat recovery process and understand the heat transfer process all in a controlled laboratory environment, but at full scale. Currently, as far as I'm aware, there's no controlled environment that this has been implemented on. So for heat, the heat transfer process is complex in servers, and therefore, if we try the test the system under various flow dynamics, under various soil types, and we can measure the thermal conductivity and other parameters as well. Also, the thermal convection between wastewater and in-sewer pipelines has been based on assumptions most of the time, and the heat exchanger itself, because it's a small confined space in the sewer, so you need minimum size with large capability of heat extraction. So the new model will look something like this, and you will account for other heat transfer processes between in-sewer air and soil, between in-sewer air and ambient air, and also the convection between wastewater and or at least investigate the sensitivity of these parameters. For heat storage, the idea is to use existing infrastructure in the sewer and develop a smart system for heat storage through real-time control, or use storage material, or a combination of both. it's estimated that heat storage material you would require around between 3 and 4 cubic meter per household to cover the annual heat demand. This is a experimental laboratory rate in Sheffield that I'm aiming to use, because what we can do here, we can change the soil, change the characteristics of the soil, we can change the thermal conductivity in the groundwater. So we study the heat transfer processes without any heat recovery, and then we can deploy a heat recovery system and a heat storage system under controlled environment. So once that's done on a single pipe, then we can optimize the heat recovery in a sewer network. And this is complex as well, because when you recover heat from upstream, that will impact the temperature downstream, and therefore impact how much heat you can recover downstream. And that is only first generation, but then you have, that's first and second generation, but then you have third, fourth, up to maybe in this network of seven generations of sewer pipe. So it can be done, it won't be an optimal solution, but we can start with Monte Carlo simulations or unit algorithms. And then once the network model is optimized, we can apply it on a field study where we monitor temperature and validate the optimized model, and also validate the business model. And once done, once implemented in a field study, it can break some barriers and be spread out on different networks in the country. We need also to review the performance and scale the potential of integrating renewable heat with other renewable sources at the time. Obviously, with something like this, we need to collaborate with water companies and consultancies and break these barriers so they're more confident in taking this on board. Also, the heat exchanger manufacturer needs to, it's a unique setting, so they need to be updated on what can be done to city council, health education, they're all important in this project, and universities as well. So to summarize what I've been saying, we need to focus on the heat balance equation and make sure that all the processes are included, and then apply a heat story using transient model. Apply all of this in a lab scale, and that will enable us to confidently apply in field deployment and also monitor the main parameters and validate our business model and network model. When that's done, then we can expand the technology and be more confident in applying in the network. And thank you very much.
Thanks, Mohamad. We've got some time for questions, so I might just flick back again to the summary. So yeah, oh, that was very quick. Right, let me come up here. Exercise. Thank you for that. Yeah.
Thank you very much. Very interesting. My name is Mohamad. I'm from Korea in Denmark, where we do optimization of wastewater treatment plants and sewer systems. In Denmark, we already today have heat exchangers at the wastewater treatment on the effluents. For some reason, they don't want to have them at the inlet, and they tell me they don't want to extract heat from the water before it enters. They don't want cold water to enter the wastewater treatment. During winter, they're very unhappy when the snow is melting, going into the sewage, cooling down the sewage, then getting slower biological processes. Have you got any idea about how much you will change the temperature of the sewage when you start to use the exchange and extract the heat from the sewage?
Yes. Well, no, in Denmark. Yeah, I mean, that is the idea of the model, is to predict how much heat you can recover without causing significant reduction in temperature. And recovering wastewater at the treatment plant, that is safe because there's no much regulations on temperature. But the problem is you don't always have consumer of the heat recovered across the treatment plant. But yeah, so the model will show you
everything perfectly. The question is how much sewage.
You just want me to do more exercise.
No, I think I understand it. The question is how much will it change the temperature of the sewage?
Yeah, so it will depend on the flow and how much you recover. But what I want to show you here is that you have a number of options. So, for example, if you are worried about the temperatures and it is winter, then you only recover 6 megawatt hours, and that will have a lot of viability. But if you increase the model has to be, or your control of how much you recover has to be dynamic, depending on ideally in a real-time control system. If your wastewater temperature is 5 degrees Celsius, you don't recover anything. But if it is 10 or 12, then you can recover upstream, and that will the wastewater will increase temperature because of the surroundings. So it has to be a dynamic control in real-time control system. Does that make sense?
Yes, makes a lot of sense. Thank you.
Okay. Mohamad, there's been other hands that have gone up, so your talks have a lot of interest. But again, I'm kind of militant with the time, so
shall we charge them?
Yeah. So after, yeah. So during the lunch and breaks, I think.
I'll be around.
Yeah, and I saw Dragon had his hand up as well. So yeah. Do you with the speakers? We're covering so many things. So lunch and break. Please continue the questions. Thank you. So our next speaker is going to be talking about groundwater management and climate change. Let me go through. So Akbar, Javadi, please come to the stage.
Good morning, everyone. I'm Akbar Javadi from Center for Water Systems. In this presentation, I'm going to talk to you about the research that we have been doing in the last 15, 16 years on groundwater modeling and groundwater management in coastal aquifers, mainly under the effect of seawater intrusion and climate change, and our journey through this process and the future direction as we see it. I would like to acknowledge the contribution of some researchers, PhD students, and academics and international colleagues in this field. My research is mainly computational geomechanics. I'm a geotechnical engineer. And since in the last 22 years, we have had over 70 researchers contributing to research in our field, in the fields of geotechnical and geoenvironmental engineering. We work in the areas of geoenvironmental engineering, geotechnical engineering, application of engineering optimization in geotechnics, geoenvironment, and also application of AI and machine learning, either as a standalone tool or integrated into computational simulations. So in this particular presentation, I'm going to talk about modeling of groundwater resources in coastal aquifers, a model that we have developed for simulating seawater intrusion, and new methodology that we have proposed to control seawater intrusion, and studies that we have done on the effects of sea level rise and effect on sea intrusion, and applications to some real-world case studies, and then I'll conclude with some suggestions for future research in this field. Generally, about 70% of world population live in coastal regions, and many of these regions depend on groundwater as main or the only, in some cases, the only source of water supply. And in coastal aquifers, we have groundwater, freshwater, in contact with seawater and saline water, separated by a zone of dispersion, which is a dynamic zone. It just moves, it's not static. And there's a growing population, and which results in increasing abstraction. And you can imagine if you increase abstraction, this zone will move towards the aquifer and salinity will intrude, causing some contamination. On top of that, we have sea level rise, which increases the head of water on the saline side, which again helps with intrusion. The problem is that very small percentage of salinity in soil, in water, can make it unusable for human use or any other use. There are many countries around the world who have either lost their groundwater resources or in the process of losing groundwater resources. So it's a very important challenge. Groundwater and aquifers are distributed all around the world, but there are many aquifers in coastal areas which are subject to seawater intrusion. And in terms of groundwater abstraction, this is a comparison between abstraction levels in 1995 and 2025. And you can see that in almost all countries, the trend of groundwater abstraction is increasing trend. So we are abstracting more and more from groundwater resources. And the climate change, according to IPCC, in the current century, it's expected that the sea levels will rise something between 200 millimeters to 880 millimeters, depending on different climate change scenarios. So in this research, about 15 years ago, we started with developing a computer model for simulating flow and contaminant transport, and then we adapted it to the problem of seawater intrusion. And we studied a lot about in this field, a lot of case studies, real world or kind of hypothetical cases. And we proposed a method for controlling seawater intrusion based on a combination of abstraction of brackish water and at the same time recharging the aquifer using some treated wastewater or other sources of water. And also in countries that suffer from shortage of water, we could have an option of desalinating the water that is abstracted and using it as an additional source of water. We have analyzed this. Also, there's another version of this, which is a very similar arrangement, but the recharge is done by gravity using surface ponds. In this case, we don't need energy to infiltrate the water. This is a method that we have proposed. Obviously, we need to know what is the optimal arrangement in this proposed method. We use some simulation optimization models, and we've compared our proposed method with some of the existing models, which are based on abstraction only of saline water or recharge of aquifer. So we applied it to a benchmark case study. These are one of the early applications of that, where we formulated the problem as an optimization problem of identifying the optimal locations for abstraction wells and recharge wells, optimum depths for these wells, what's the optimal rate at which we can abstract water and recharge to minimize the cost and minimize the salinity in the aquifer. Of course, subject to some practical constraints. And this is some of the preliminary results we obtained. If we take obviously no action, there's no additional charge. The normalized value of salinity in this particular case study would be something like 167. With abstraction only, the optimal arrangements requires an abstraction well 90 meters deep, 50 meters from the shoreline, abstracting, say, 0.08 meter cube per second. That reduces salinity from 167 to 149 at a cost of $2.6 million per year. Similarly, recharge method, which is a conventional method, requires an optimal arrangement shown here, but reduces salinity to 151 at a cost of $5.7 million per year. Our proposed method requires an abstraction well in conjunction with a recharge well, but reduces the salinity significantly more to 142 at significantly reduced cost. So if you can compare the cost directly, our proposed method ADR, the one on the bar on the right, is about half the cost of abstraction only and about a quarter of cost of the recharge only. And it pushes the interface between freshwater and saline water further towards the sea, protecting the aquifers very efficiently. We have done similar applications using multi-objective optimization, as we have two objectives here. I'll probably skim quickly through this very similar optimization arrangements, but this time using a pond rather than injection wells. And similar comparisons, but the advantage here is that we get a pre-to-front, which is basically a number of possible solutions, optimal solutions, from which we can choose. Again, we have shown that our proposed method, abstraction, desalination, and recharge, results in much reduced cost and much reduced salinity. Also, in terms of a study of sea level rise and effect on seawater intrusion, we have looked at different scenarios, the effect of sea level rise based on just increasing head of water on the seaside, without considering the flooded land due to sea level rise. Also, the effect of land which is flooded here. As sea level rises, depending on the slope of the shoreline, a large area of land can be flooded, which practically moves the interface further inland. And also, we have looked at combined effect of sea level rise and over-abstraction from groundwater. So this is one of the case studies we have looked at. This was a study we did in 2014. This is the kind of steady state current situation in 2014 in terms of distribution of salinity. And we chose a kind of a scenario for sea level rise, assuming that by end of the century, in 100 years, about 65 centimeters of sea level rise we will have, which is within the band of IPCC prediction. So this shows the kind of gradual movement of the interface between saline water and freshwater over the century, just assuming that the increase in head of water, ignoring the flooded land. But if you consider the effect of flooded land by sea level rise, depending on the slope of the ground, as you can see, the shallower the slope is, the larger area of land is flooded, and this interface will be moving further and further inland. And if you combine this sea level rise with a relatively moderate lowering of groundwater levels due to over-abstraction, something like 0.6 meters over a century, which is not unreasonable, you can see that the effect will be significantly more. Almost majority of the aquifer area or volume is contaminated in this case. And if you consider the effect of combined effect of sea level rise and over-abstraction at the top with just sea level rise here, you can see that sea level rise and groundwater over-abstraction could have very detrimental effects on groundwater resources. We have applied these methods to a number of case studies in United Arab Emirates, Nile Delta in Egypt, and Pingtong Aquifer in Taiwan. And we have lots of publications. I can't go through some of these, but they are available from our papers. But future work in this direction. One of the important points to consider in terms of groundwater management is groundwater systems are not isolated from surface water. Any realistic management of groundwater should consider the interaction between groundwater and surface water. In the Taiwan case study, we tried to look at effect of flooding and seawater intrusion and how we can work one against the other, how we can solve two problems, manage the flooding and seawater intrusion together. Some of the models that we have been developing are very computationally intensive. So perhaps surrogate modeling and use of AI will be very efficient use of computational time. We have done some use of surrogate modeling, and we have shown that computational time can be significantly reduced by surrogate models without compromising the quality. And we have got some papers on this as well. Any modeling of groundwater, management of groundwater should consider uncertainty. Ground is a very variable medium. The properties of soil can change from one point to another. The type of soil can change from one point to another. We have a lot of uncertainty about climate change scenarios, rainfall patterns, change in rainfall patterns. All of this brings uncertainty that should be considered in analysis. We have got a recent PhD which is completed looking at uncertainty analysis. And with the kind of development of sensing systems, IoT and digital twins, perhaps in the future, sensing, using sensors, IoT, and digital twins, using some of these models combined with the real-time measurements would be very valuable tools so that we can monitor the groundwater resources in real time using very accurate models and make predictions for future. Thank you very much for your attention.
Okay, brilliant. So we've got time for a question if we've got any. I'm going to do my classic, go back in the slides. So if anyone's got a question, if you want to raise your hand, and then I can come over. Anything? Otherwise, we'll crack on, then we'll be ahead of time. Okay, we're going to go ahead of time. But yeah, you're around for the rest of the day, aren't you? Yeah, perfect. Thank you. Okay, so we've got our final speaker now, who's going to be talking about extended reality in water research and education. So Albert Chen, there you go, over to you.
Okay, good afternoon. Good morning, everyone. Yeah, so I'm Albert Chen. So it's my pleasure today to share with you what we are thinking in Center for Water Systems about the future using this extended reality to enhance our water education, research, and perhaps also can be used for industrial application. So what's the extended reality? I don't know if you are all familiar with that. So now we've seen quite a lot of applications about this virtual realities, and that's using that to put you in some virtual environment to sense what's the particular scenario you won't be able to see in your real life or directly. So that could be one of the things you might be familiar with. And the other ones you might be familiar with the Pokemon Go. That's the augmented reality to help you to do something. And could that be used for our water education or research? And there could be also some a little bit fancy that to assist the reality, this combination of the actual reality with some augmented reality. So can we combine together, or even further, if we can have the mixed reality to have the virtual world and embedded with augmented world to help you to better understand some particular challenge or help you get through some particular process. So that's how we can see it. On the left-hand side, you can see the real world is what the practical physical environment we are situating in. But on the right-hand side, there could be some virtual reality, virtual world, totally like a built computer, and by computer in some world you might not be able to really be positioned in. But that will, because using some technology will allow you to experience that. In between, we can introduce some additional sense in this world. So we can add some visual, so you can see some real world things and combining some virtual stuff. Or you can also have some audio sound getting into. So this are quite often also has some kinetic movement that can detect what you're doing, and that the system will react and to see how will you respond. So this kind of technology is being quite widely applied. So I think most of us are not suitable for this kind of theme park adventure. But now, if you have some opportunity to go to the theme park, the Disneyland, Universal Studios, so that they have some sort of new experience. You can do that, and even have they call 4D environment. So it's kind of mixed the reality to help you to to increase your experience, and maybe also that can we use that to help us our learning. So now, why is now it's more popular? Because now there's a lot of emerging technology make it more affordable. So we can have different headsets now. It's available market at a reasonable price. So it's not 10,000 pounds for one gadget for those flight simulator for the airline company that train the pilot. Now we can just put on the headset using the Meta Quest, or using the Vive, or using the new one, this coming one, the Apple Vision Pro. So there's a various appliance that could allow you to do this kind of activities. So can we take this advantage to help us in our research, in our training? And the other thing is that if you look into the literature, so that's some trend. So the one is the Google trend. So how people are interested in this virtual reality or augmented reality. You can see the red line. There's the Google search about augmented reality, and in the blue lines there is the people's interest about the virtual reality. You can see this in general. This augmented reality has got more interest because we all have mobile phone. We can play Pokemon Go. So people get familiar with these kind of things. And now, but you can see also both augmented reality and virtual reality been more popular getting more popular in the last couple of years. And if we look into the research side, how can we use that for the education? So there are also the literature review about the papers that have been talking about using the augmented reality in education, and also using the virtual reality in education. That's getting more popular because the affordability of the technology. So can we really embed it in our water research and education? So, and if we look into the future, so there's the projections. So how this extended reality include all the reality I said earlier. So you can see this projection for the market is growing exponentially. So people will be taking more and more applications. And can we take the advantage to help us improve our work? So there's the other things. It's not just because things that is trendy, is popular, so we need to do that. We are thinking why it's really benefiting us. So we look into some studies. So there's some studies that, and when we're using this virtual reality or augmented reality to train the staff, engineers, they are more. They will be faster to complete the training to do the same thing in the classroom. So it's 4 times faster because it's more accessible, and the procedure is more streamlined. So that will be beneficial for us to train the students, or train the company for the company to train the engineer to make things more efficiently. And also there could be people will be more focused. So because this kind of environment, this kind of technology require your full concentration. So you don't have time to wear your headset while you're still swiping your mobile phone. So it's no doubt. So people will be more concentrated, more engaged in this learning process. That will lead to better learning outcomes. And that's also another reason that's the people, when we put people in this kind of immersed environment, they are more emotionally engaged through the process. So then the in the classroom, they might be distracted by something else, so they're not so emotionally engaged, connected through this procedure. So that will certainly affect how the effectiveness of the learning outcome. And the final one is that it's also found that if we use this kind of technology to help the training and go through the procedure, people, they are more confident to use the skill learned through the training in the applications than those one who haven't done any training before. So that's the benefit. We use that to help us to do our research and the training. And the other thing is that we got all this university got this very fantastic facility to do the experiment for the students, but each of this equipment requires space. So how much space do we have? We can only have 1 or 2 flume in any of the university. Not the university can have 10 or 15 flumes. So, but I have 50 students in my class. So how can I train the students with one single flume? And each single flume, we need to do various experiments, open channel and weirs, sluice gates, dam, etc. So there's so many that require a lot of time and the space. So can we achieve that with using the technology instead of you simply rely on this equipment, physical equipment? I'm not saying that's not good. That's fantastic for helping people for learning, but because of the time and the space we have, so how can we utilize the technology to accelerate the learning process? And another thing is that more importantly, we in the last couple of years experienced pandemic. Even though we have space, we have time, but we cannot access the facilities. And also that could happen if we have some disaster. We had some colleagues that in Turkey, they have the huge earthquake, destroyed all this infrastructure. So those facilities won't be available for the students. Though we cannot let the student to wait for another 4 years for everything being rebuilt and then they come back to learn. That's too late, a waste of time. So that's why we need to think how can we embrace the new technology helping us to improve the learning in the education. And also beyond that, we also need to use that to do the research. So how can we try to take the benefit of doing our research as well? So we think how can we do that? So we can utilize this XR in water education and the research. How can we use that to improve the knowledge of the students and they can help them to learn the theory better or understand the procedure to do some research or some work? Or can we improve their skill using this technology to improve their skill in terms of operation of systems or try to analyze this phenomena of the hydraulic situation in order to make a better judgment? Or can we utilize this technology to help them to improve their competence? So they will be able to design a system and make applications for their practical work. So here I'm just trying to give some very quick small examples that illustrate what could be done. So here is this example that we have the flume in the screen, and you can see in the photo we have this physical experiment that's allow the water going through the weir. But for students, we need to explain to them and how to observe how this there's different flow conditions. So when the upstream flow, we have the subcritical flow condition with slow movement water with deep water depths and going through the weir and becoming supercritical flow on the right-hand side. And this we use the augmented reality or assisted reality. When students, they are doing this kind of experiment, we can show the streamline like this and also show the movement. Let's do this again. So let's show the movement of flow, help them to observe and so compare. In theory, you should observe something like that. That's what you observe. And also we can pose the question to them. So what's the water depth? You will observe this water depth here. So you need to do the calculation at the same time and to estimate flow number in order to judge that is there's the subcritical flow condition or supercritical flow condition. So let's try to mixed all the physical experiment and also this kind of setup, so to accelerate the learning to better understand the phenomena. And the other one is that if we look into the virtual reality, so this is the facility. If you if been away from Exeter for a long time, so that's our new facility, fantastic facility called V Simulators. So it's a lab. So you can have people standing on this platform and they put the VR headsets on, and then you will be able to see an environment, the virtual world like this, and the platform will move. So to mimic the vibration of the environment, so that we will be able to observe people's behavior. If you are walking on this the bridge, the wobbling bridge, so how will you react? Or if you are walking on different environment, standing on the boat or sitting on the train, and how this will affect the different environment condition will affect your movement, and in order to help us to better design our infrastructure. So this is for the structural engineering college. They're doing this, but we are thinking, can we also utilize this to see how people will react if we put them in some flooding situation? So it's not safe for some. If some of you might have seen Sobodan's presentation earlier, that some colleagues they very bravely put out their students caught in the very fast moving flume to see people's react going through the flood water. So can we use this kind of technology to in a safe environment to observe people's behavior, and then so then the other things that if we have imagine if we have some in the underground stations, so there's a flooding, so coming from the state to the underground station, how people will react to evacuate safely in this kind of stressed conditions. So that's can we utilize this kind of technology to help us to do this kind of research? And the final example here is that can we use this to help the training operations? So on the right hand side, there's some digital combination with the digital twins. So when we send the engineer to the site, they will need to fix something, but they don't have understanding of what's underground. Or can we use combine the digital twins of augmented reality to show what's the pipeline condition underneath the ground, and what's the is there any electric pipe or gas pipe associated? And on the left hand side, you can see another example is from KWR. They're doing this similar augmented reality to help the engineer to better understand the situation they're working on. So there could be some benefits for us to look into the future to support not only for the teaching, not only for the research, but also for the industrial practical applications. So this just want to conclude my talk here is that I want to invite you to share your opinion with us in the workshop later. So we have the workshop in the exploratory labs too. So it's on the first floor, and so we will listen to your opinion. What's your vision of the future to use this extended reality to help us in terms of the research, in terms of teaching, in terms of industrial training or applications? Thank you very much.
That's brilliant. I mean, we've got time for one question, if there's any burning questions. Otherwise, we can use the break. Oh, yeah. Go on, Fayyaz. Yeah,
play with this one. Don't do this.
It's the purpose.
Can you hear me? Quite impressive presentation, I think, and very futuristic as well. Do we have any thought on the barriers to achieve that kind of restoration in terms of, I think finance is going to be the major barrier. Any thoughts on that?
That's a good question. So that's what I want to pose to you for our workshop discussion. But indeed, there's a various barrier we are experiencing now. So first of all, most of us, I believe, most of us are water engineers. So how are we going to translate our knowledge into something using different technology we are not familiar with in order to help more people. So that's the one thing I would like to start with. But I would like to invite more of you to come to give us your thoughts later.
Great. That was a great hook.
Thank
Well done,
you.
Albert. Thank you. Okay, so that leads us nicely on to, we've got a couple of pictures for the workshop. So Pete, would you like to